In this section of the tutorial, we're going to look at vectors that change in time and discuss how you compute their rates of change. Let me begin by reminding you of something that you've already seen previously. Namely, when you have a vector that changes, you can compute the net change in the vector by taking its final value minus its initial value. So for example, if here's a vector A, and this is what it looks like at a particular moment in time, t, and then at a later time, let's say at a time t plus delta t later, so delta t represents some time interval later, the vector has changed, and now this is what it looks like. So to compute the net change in the vector, we put the two vectors tail to tail, and we subtract them, and this red vector is what you get when you subtract the final vector at the later time minus the initial vector. And so this change in the vector, I called it delta A, that represents the change in the vector during that time interval. Okay? So formally we would say that delta A, the change in the vector, is equal to the vector at time t plus delta t minus the vector at time t. So delta A describes the net change in the vector during that time interval delta t. Here's one simple yet important example of that. Suppose I have a particle and it's moving along through space along this curved red dashed line here, and there it is at a given moment in time. So we can define its position vector, labeled r here, to be a vector that points from the origin of this coordinate axis that I've drawn to where the particle currently is at time t. And so as this particle moves along this path here, the position vector, which points from the origin to where it currently is going to be varying. So whenever a particle moves, its position vector changes in time. So suppose, for example, that at some initial time, the particle was here, and so I drew this position vector pointing to the current position of the particle at time t sub I. That's time t initial. Then at some time later, the particle has moved along and it's gotten to this point. So here's the new position vector, the position at time t final. So the net change in the position vector went from here to here. So what I've drawn here, this red vector, is the difference between the two vectors. It's the final vector minus the initial. And so I called it delta r. It's given a name. It's called the displacement vector. It tells me the net change in the position of the particle. So anytime you have a vector that changes in time, it's very natural to describe the rate of change of the vector. And that's what we'll do right now. So let's once again consider the vector A. At time t, here it is. At a later time, it's here. So the change in the vector between time t and time t plus delta t is given by this red vector right there. So delta A is the change in the vector. Okay? And that change occurred over a time interval delta t. So we can define the average rate of change of this vector during that time interval to be the change in the vector, delta A, divided by the time that it took that vector to change, delta t. And so here's delta A. It's the final vector at time t plus delta t minus the initial vector at time t. So the change in the vector divided by the time interval over which that change occurred, namely delta t. So once again, this is how we define the average rate of change of a vector during a time interval. It's the change in the vector divided by the time interval. Now, often in physics, that's not quite good enough. You may not want to know what's the average rate of change of the vector over some long time interval. You want to know how it's changing right at a given moment. So what we can do there is we can shrink down the time interval that we're looking at the vector over and define what's known as the instantaneous rate of change of the vector. So rather than telling us the average rate of change of the vector over some long period of time, we can say in this very short time interval, how is the vector changing? And we define it as follows. We just shrink down our window of observation, delta t, and let it go towards 0. So mathematically, we would write this as follows. We want to take the limit as delta t goes to 0 of the rate of change, average rate of change of the vector. And this gives us what's known as the instantaneous rate of change of the vector. And for those of you who have had calculus, you'll recognize that this is the derivative of the vector. So this is how we define derivatives. If you are taking a calculus-based physics class, we'll talk more about this, and we have a whole tutorial on calculus upcoming. If you're not taking a physics class, a calculus-based physics class, then just think of it as follows, that this is the symbol that we use to describe the rate at which a vector is changing in time. So, dA dt represents the rate of change of a vector. It's the time derivative of the vector, and it tells you how quickly it's changing at a given moment in time. And in particular, dA dt is itself a vector. So it's when you take the derivative of a vector, you actually get another vector. And it points in the direction that the vector is changing in. And the size of this vector dA dt, or the size of the rate of change of the vector, describes how quickly that change is occurring. Let me just re-emphasize, if the physics class that you're taking is not calculus-based, you don't have to worry about this weird symbol that we use to denote the rate of change of the vector. Just recognize that this is a vector, and it's telling you how quickly the vector A is changing. Okay, so one of the most important examples of this is the velocity vector, because if you have a position vector that points to where a particle is, then as the particle moves through space, so again, let's imagine that a particle is moving along this blue curve here, and let's say at a given moment in space it happens to be right there. So r is its position vector right at that moment. But obviously, as this particle is moving along, it's changing its position. And we define the velocity vector to be the rate of change of the position vector. But again, you don't really have to worry about this as an entity from calculus, because just think about it intuitively. The velocity vector is a vector that points in the direction that the particle is moving in. So picture a particle coming along here. It's traveling along this blue curve, and right when it gets to here, you see how it's moving in this direction, indicated by the red arrow here. So the velocity vector points in the direction that the particle is moving in. Formally, it's the rate of change of the position vector, but intuitively, it's simply telling you the direction that the particle is moving in at a given instant in time. Okay, a few comments on this. The size or magnitude of a velocity vector is simply called the speed. So this is familiar. How fast is something going? So you don't worry about its direction. You just, if you want to know just how fast is something going, that's called its speed. And so the magnitude or the size of the velocity vector is called the speed, and the direction of the velocity vector tells you the direction that it's moving in. Secondly, we just saw that when the position of a particle varies in time, then the rate at which the position changes, namely dr dt, that's what we call the velocity. But sometimes the velocity of a particle is itself going to be changing in time. I mean, just think about it. Suppose you're driving in your car. Sometimes you go fast, sometimes you go slow, sometimes you might be heading north, then you might turn the steering wheel and you might be driving east. So your speed and direction can change. In other words, anytime your velocity changes, either your speed or direction, in other words, anytime you have a change in the velocity vector, by definition, we say that you are accelerating. So acceleration means that the velocity vector is itself changing. And we define the acceleration formally to be the rate of change of the velocity vector. So the acceleration vector is the rate of change of the velocity vector. So one final point. Suppose you're given a vector that's varying in time and you want to actually compute its rate of change by actually taking a derivative. How do we do this? Okay, in other words, how do we calculate the derivative of a vector? For those of you that have had calculus, you know how to take derivatives of ordinary functions, but how do you take the derivative of a vector? Well, it turns out it's really, really simple. Okay, so let's say I have a vector and I've written it in terms of its xy components. So for instance, let's say here's a vector A, and it depends on time, and it's given by this amount in the x-hat direction plus this amount in the y-hat direction. So notice that the vector depends on time. So the x component of the vector is changing in time. It depends on time. And likewise, the y component of the vector changes in time. So here's a vector. And if I say, let's take the derivative of this vector, in other words, let's find the rate of change of this vector, how do we do that? Very simple. First, you look at the x component of the vector, namely this part here, and you just take the derivative of the inside here. So the derivative of 5 plus 3t plus 9t squared is 3 plus 18t. If you don't remember how to get that, you can review the calculus tutorial. But if you do, it's just taking the derivative of the x component. Then you separately you go to the y component. 2 plus 6t, take the derivative of 2 plus 6t. With respect to time, you get 6. So this then is the new vector. It's the rate of change of vector A. And that's how you take the derivative of a vector. Likewise, you can integrate vectors too. You take the x component and you just take the integral of the inside, and then separately you take the y component and you integrate that.